Sorry for the technical difficulties, but now we'll continue. So before we get into the specifics of our individual work, we would first like to present the progress of the V8 RISC-V porting effort as a whole. So here we have a more detailed diagram of the RISC-V porting progress, which describes the roadmap that is more particular to the specific goals by us in Rios that we would like to achieve. So the first two stages, which is the setup and the enable compiler and assembler backend stages, are actually more common with the RISC-V porting effort as a whole. And these two stages represent setting up the RISC-V 64 backend, running tests on the simulated build, as well as successfully cross-compiling V8 into RISC-V binaries. So the second stage also contains work which we have done to enhance the RISC-V backend by introducing different extensions such as the A extension and the C extension. So the progress within these two stages are very high, and we are able to pass 93% of the V8 test cases on the simulated build, and we already have regressions running on real hardware. And also we are well on our way to finishing adding the A and C extensions to the backend. So the final two stages, which are enabling high-level features as well as making the Chromium work, are steps that the Rios lab specifically have taken charge to work on and represent both future and current work. So up next, I'd also like to present the upstreaming status of the V8 group. So long story short, we are very close to pushing our RISC-V port to the master repository. So on the right, we have a diagram of some of the different actions we need to finish in order to have a successful upstream. The green boxes represent actions that we have passed already, and the yellow boxes represent ongoing work. So for example, we have a full set of tests run on their required architectures, and we also have some logistical items, such as all authors signing the Google CLA finished. On the other hand, we have other ongoing work, such as rebasing to the tip of the branch. So for this, we actually only have a few issues that we need to resolve that we got after rebasing. And in fact, since we already have a pull request on the main branch for our code, once we resolve these issues, all we need to do is really wait for a reply from Google. And since we last communicated with Google, we actually had very few comments about changes we had to make. So we are very optimistic about the port being pushed upstream soon. So finally, I would like to explain a bit about the 2021 wish list that the RISC-V V8 porting group has compiled together. So the items detailed here are items that we would either like to finish this year, such as the C ISA extension support, as well as other items that we would like to start working on. So next to the items, I also added the names of the groups that are currently undergoing work towards the item. So for example, our lab, the Rios lab, is working on the A and C extensions, as well as porting Chromium. And we also have the PLCT team working on things such as performance tracking and code performance speedup. Alongside this, we also have the ideas of adding TensorFlow and Node and Chromium to our repertoire of demos, as well as adding the LVM compilation process to the V8, to the RISC-V V8 compilation process. So now that we've explained a bit about the V8 progress as a whole, we would like to start talking about our individual work. So as a baseline, it currently consists of the addition of instruction support for the RISC-V 64 A and C extensions. In this case, it really means just adding to semantics for the extensions to allow V8 to understand the A and C extensions. So we basically use this as baseline work in order to help us with our now ongoing work, which can be split into three different parts. So the three different subjects that we're currently working on are the WASM atomic support, finishing adding the C extension to the turbo assembler so that we can get compressed in smaller binaries, as well as deploying V8 onto the PicoRio. So the main reasons why we decided to work on these features is that it allowed us to become more familiar with the V8 environment as a whole. So we were able to touch upon areas such as the assembler with our work on the A and C extensions, and our work on the WASM area has helped us understand the parsing and decoding of the turbofan compiler. So furthermore, our work has also helped introduce us to other areas of the V8 environment, such as register allocation during code generation. So in the next few slides, we would like to explain a bit more about working on the different features, why we decided to do so, as well as some of the ideas that came from them. So for our work on the C extension, I would just like to explain out of why of all of the features that we could have worked on, we decided to choose this one to work on. So members of the PLCT team helped to develop some tools to help collect information about instructions run for certain for run binaries. So we use these tools to help support our decision to add the C extensions. So we took two benchmarks that are currently available for V8, Kraken and Spider, both of which SunSpider, both of which are benchmark suites that have a focus on real-world applications. And so we took the printed code for each benchmark and figured out the percentage of instructions that could be converted to C extension instructions. Amazingly, the ratio of instructions that are convertible are around 40% to 60%, and it's a very big performance improvement. So it helped support our decision to add the C extension as soon as possible because it was a low-hanging fruit that would have great performance increases. Once we get more tools to help us understand the generated instructions, I would like to see how helpful the addition of other extensions might be. So after adding the C extension, we decided to try following a similar path to increase code quality, which ended up to us researching on changes to the register allocator. So on the right, we have a diagram showing the whole flow for our code generation. So our research right now would focus mainly on the register allocator algorithm itself. Currently, the register allocator algorithm employs either a linear allocator or an experimental greedy allocator that's also used by the LLVM. So we feel that this is an interesting avenue to explore because the algorithms were really defined for general architectures, and we would like to explore changes that could, for example, make the heuristics and live range analysis different of the algorithms different to increase code quality for certain RISC-V applications. We would also like to explore changes that could help take advantage of certain architectural features of RISC-V, or to take advantage of RISC-V's extensions, such as its C extension. So the main reason we decided to take a first look at the register allocator was because it was the most understandable next step as a step up from the addition of the C extension, seeing as how the C extension is very affected by how the registers are allocated. And also, we feel that it is the area that is most easiest for us to understand at the moment.
Okay, that's my part. WebAssembly is also an important working direction for us to find better support for the engine efficiency, the testing, data for the testing. We have to pass almost 90% as basis. And they don't remain out as basis. The WebAssembly related issue is nearly 1/3. So WebAssembly is a major outcome this 5 issue for the engine. And from the other point of view, WebAssembly is a relatively lower level representation for binary code for the engine. And those lower level semantics enable better application. We can make use of the simpler in supporting the WebAssembly autonomy operation. Yes, WebAssembly product has been one. WebAssembly is one of the important features for JavaScript because JavaScript is single-threaded, but WebAssembly enables the novel features, including aggregation, multi-threading, cookie, etc. for single-threaded JavaScript. So this is in some ways an extension for JavaScript. So we are supporting a target operation for WebAssembly. First of all, have supported an assembler simulator activity test for the intended to enable 3D are currently working on some applications to enable the consolidation part. We have started with the low user and low additional part instruction, and we are working on the ANU part. In the future, we are going to fabricate the semantics with the multi-threaded bid execution. This methodology is also similar to our porting methodology from bottom to the up to find the high-level JavaScript API. In the third, we have been working on deploying data into PicoRio citizen. This has made the first hypothesis that data only depends on the new DC and the kernel have to the problem with high penetration and suitable supply. And we then for the state to PicoRio 4. It was fine to also based on quantification and recommendation for either including the add expansion. For example, we have once disabled that expansion. This is a figure for demo of bike, and then I will present the live demo to show how to use PA or, by the way, no. Okay. And then switch the window and from the left-hand side, this window is a QMU image. And we can see the cache. Oh, this is a risk by the environment. Thank you very much. And we can our executable here. We can use .da here, and we can make use of the JavaScript semantics. What? This is a really flexible JavaScript program. Okay. Sorry. By the way, we can also demonstrate Node.js because this part of job has been done by our colleagues from BLCE team. This is a Node.js. It supports actually the JavaScript syntax. Okay, sorry. We can also present it. Maybe we need to console. Sorry, this is a kind of non-supported feature. Okay, but we can still present some basic arithmetic calculation. And we can provide. Okay, that's all. And from the other side, okay. This is a QU demo, and in the development environment, we have make use of the V8 simulator to enable the efficiency for debugging. And because this is our x86 environment, and we have make use of the simulator. The simulator simulates the RISC-V instructions executing on the x86 environment. So we can make use of APIs as well. And we can make use of it. Okay, that's actually we can download it. So back to the slide. The final slide showing our future directions. We can divide this into three categories. Firstly, we want to provide better support for ISAs and WebAssembly and other things, and to improve the JIT compilers for higher quality. And we are going to explore the chance to better register allocation, and just mentioned by Dereck, and we are going to make use of the TurboFan IR. The TurboFan is the internal compiler in V8 engine, and this IR may be used by the previous binary translation project as a backend. So what's more, we are going to interrogate the thing with other real software projects, including Chromium OS and Chromium web browser. And this is a really fantastic job for us to construct a better software ecosystem. Thank you very much. Sorry for the sound quality. Any comments or suggestions for us? We are really appreciative for that. Any questions? Okay. For we need to develop the thing in our own PC environment, which are normally macOS or Linux macOS based on x86 or ARM. So we cannot debug and code efficiently in RISC-V simulated environment. So the simulator is used to something like interpret and decode the RISC-V instruction generated by V8 engine to some C function model based on x86. Okay, we can discuss this later. Thank you very much. Okay.